I'm Kevin. Welcome to my cave. As I was working on the script for this video, I realized that last time I talked a lot about biasing transistors, but I didn't define what that is. So I'm going to begin this episode by backing and filling, defining biasing, and showing a shortcut that's often useful in designing transistor circuits. Biasing refers to adding a constant DC voltage to our signals, so as to bring them into a convenient range for our circuits. It's putting a thumb on the scale, so that AC signals such as radio and audio signals, instead of oscillating around ground, oscillate around some other voltage. Let's look at a concrete example to try to explain this. Let's say that we want to design an emitter follower like the one we were looking at last time. We want to match an audio source with a 10 kilo ohm impedance, and we need to drive a load with a 4.7 kilo ohm impedance returned to ground. We have a single 12-volt power supply available. Obviously, we're going to need an impedance matching circuit here. If we were just to connect the input to the output, we'd be creating a voltage divider. The voltage coming out would be only about a third of the voltage going in. So that's a bad idea, and we do need the emitter follower. The voltage on the transistor's emitter can never fall below ground, because the emitter resistor can only sink current, not source it. And that's where biasing comes in. We need to shift our signal toward positive voltages, so that the output voltage stays in the range that our circuit can deliver. So let's put a big capacitor at the input, and another one at the output. These capacitors are called blocking capacitors, because they block the DC voltage. They're also called coupling capacitors, because they couple the signal into and out of the circuit. It all depends on your perspective, I guess. We will make these capacitors so big that they look like short circuits at signal frequencies. The output capacitor forms a high-pass filter with the load. We need to make it big enough that the corner frequency is well below the audio range. I'll choose 2 Hz as the corner frequency. I'll round up the capacitor value to one that I know I have at hand and use 22 microfarads. Now let's work out the biasing. The specific bias voltage isn't terribly critical here. We'll choose a voltage halfway between the power rails, which will allow a pretty big output swing. The blocking capacitors block DC, so we can ignore them and everything beyond them when we're setting the DC bias. We will need to choose what current the follower will draw when there's no input signal. That's called the quiescent current, and I'll denote it I sub Q. I'll arbitrarily choose half a milliamp. I'll have more to say about how to make this choice later. We choose the emitter resistor to pass that much current at the bias point. 12 kiloohms is the calculated value. We have to set the emitter voltage by putting the base diode drop above it. We'll get that voltage from a voltage divider. The voltage we need gives us the ratio of the resistors. The Thevenin equivalent resistance of the divider has to be much less than the load it's driving, which is the resistance as seen looking into the base. And we learned last time that the resistance looking into the base is the emitter resistor times the transistor beta plus 1. We know that a small signal beta is at least about 100. I'll make it 99 so that beta plus 1 is a nice round 100. We'll say that much less than means at most 1/10 of the value. And then a few moments with algebra kicks out our resistor values. All that we have left to do is choose the value of the input capacitor. It will form a high-pass filter with whatever input impedance all the stuff to the right of it presents. Because the input capacitor blocks DC, we don't care about the DC voltage levels here. It's easiest to figure out the impedances by working backward from output to input. We're given what the impedance of the following stage is. We've made the blocking capacitor big enough that it looks like a short circuit at signal frequencies. The load will appear in parallel with the pull-down resistor. We know how to compute the resistance of 2 resistors in parallel. In the analysis, replace the 2 resistors with the equivalent value. We showed last time that the impedance looking into the base of a transistor is beta plus 1 times the impedance looking out of the emitter. So in this case, the base circuit will see 100 times the effective emitter load, or 338 kiloohms. We can take a shortcut with the voltage divider. When we designed it, we targeted to a Thevenin equivalent resistance of 120 kiloohms and an equivalent voltage of 6.6 volts. No need to recompute them. And we can ignore that constant voltage because the input capacitor will be blocking DC. Just pretend it's ground. Once more, we've got a pair of resistances in parallel, and we know what to do. I actually don't like this result very much. It's a little short of 9 times the source impedance. I usually like a much higher impedance coming in. Put a pin in that. We're not done with emitter-follower biasing. But for the moment, we'll keep going with what we have. Let's add the blocking capacitor now. Once again, we've got a high-pass filter. Once again, I'll design to a corner frequency of 2 Hz. I get a desired capacitor value of a little under a microfarad. A bigger capacitor is fine. I know I have a whole lot of 1 microfarad ones in my box. I'll use one of those. And there's the whole design of our follower. A blocking capacitor on the input, a voltage divider to generate our bias voltage at the base, the transistor itself, wired as an emitter follower, an emitter resistor to set the quiescent current, and another blocking capacitor to keep our bias voltage out of the load. And our load sees almost 90% of the input voltage, rather than only a third of it. I'm planning to show a few more follower tricks, so I'm not going to build this in the cave just yet. Let's go over to Paul Falstad's Circuit.js program to simulate it. Link down in the doobly-doo. Okay, here I am on Paul Falstad's site, showing the circuit in simulation. The simulation shows the output sitting at about 88% of the 1 volt input, which is just about what we calculated. How will it do at higher input voltages? Let's try 1 volt peak, 2 volts peak to peak. Looks pretty good. How about 3 volts peak to peak? That's still fine. What the heck? We should be able to handle at least 6 volts, right? That's only half the supply voltage. Nope. That's clipping pretty badly. For the reason we saw before. The 12K resistor can only pull down a certain amount of current. At the bottom of the cycle, the transistor's cut off entirely. And that 12K resistor is pulling as hard as it can. But negative 1.66 volts is as low as it can go. And that's because we made a subtle mistake in the biasing. Let's look at the choices we've made for the output circuit. Our problem is that we began by setting the emitter bias halfway between the power rails. To get the maximum possible output swing, it needs to be halfway between the maximum and minimum possible values it can have, and the minimum is nowhere near the lower power rail. But what's the value of that minimum? It turns out that it interacts with the value we've chosen for the emitter resistor, and that was determined by quiescent current. So maybe quiescent current wasn't arbitrary after all. Let's try to set the input voltage so that the transistor just barely cuts off on the most negative swing. The emitter voltage will be whatever we chose as the quiescent voltage, minus half the peak-to-peak signal voltage. And we said that the transistor is cut off, so it's sourcing no current. We can just pretend that it isn't there. Ohm's law gives us the current in the pull-down resistor. With the transistor out of the picture, there's only one place for that current to come from, the load. And Ohm's law there gives us another equation for the current. Grinding the algebra on those two equations gives us an equation for the emitter resistor. But we still don't know what to choose for the quiescent voltage. Or do we? We still haven't considered what happens on the most positive swing of the signal. The transistor can't be allowed to go into saturation The voltage at the most positive swing has to be a little bit below the collector voltage. Let's say half a volt. The emitter resistor and quiescent voltage then determine all the component values on the input side. I threw together a quick spreadsheet so I could play around with values. I'll put it on the project GitHub. Link down in the doobly-doo. I put all the equations into a spreadsheet so that I can play around with different designs quickly. Let's try to set up a follower for 6-volt signals, using what we just derived. We'll assume a typical general-purpose transistor with beta about 100 and a 600 millivolt forward voltage drop. We're running off a 12-volt supply. We're assuming our input is 6 volts peak to peak, but I'm going to be conservative and ask for 8 volts. We want to go down to 20 hertz signals, and we're deriving a 4.7 kilo-ohm load. The sheet tells us that the emitter resistor can be up to about 4,100 ohms. I'll pick 4.3K. It's a standard value. Our output coupling capacitor needs to be at least about 16 microfarads. I know I've got dozens of 22 microfarad ones on hand. Now I'll focus on the lower left part of the sheet. I haven't discussed bootstrapping yet. The left column gives me the values for the divider resistors. I'll use the nearest standard 5% values. The input coupling capacitor needs to be at least 2.26 microfarad. We can shade that a tiny amount. I have lots of 2.2 microfarad ones. Let's jump over to Paul Falstad's site and fill in the values. Well, what do you know? Past Kevin was kind enough to type them in for me already. And I've seen worse. The output isn't clipping anymore. Looks like a nice clean sine wave. But the circuit is only putting out about 4.6 volts peak to peak. There's always got to be some loss in a follower. But I'd like to get the output voltage to within about 10% of the input. Can we manage it? The loss of voltage is taking place because impedance is mismatched at the input. The spreadsheet calculated an input impedance of only about 35 kilo-ohms. That will knock the voltage down to just about the level we're seeing. Most of that problem is coming from the divider. The spreadsheet tells us that its Thevenin resistance is about 42K, while the impedance looking into the transistor base is about 220K. And all that the divider is doing is providing DC bias for the transistor. If only there were a way to hide it from the AC signal path. It turns out that there is a way, and it's quite clever. It's not too different from what we've already seen. We are still faced with the same relatively high impedance source. We'll still couple that source to the base of the transistor with a capacitor. We'll fill in its value shortly. The load and the output coupling capacitor are the same. The pull-down resistor still draws the same quiescent current, and the transistor is still connected as a follower. The bias network is slightly different. We still have a divider that generates the DC voltage at the base, but its resistor values, and therefore its Thevenin resistance, are half what they were before. The other half of the needed resistance is simply supplied by a series resistor. But here comes the trick. We connect a capacitor from the transistor emitter to the middle of the voltage divider. This can have no effect on the biasing. A capacitor is an open circuit at DC. But look at the situation at AC. The base and the emitter of the transistor are one diode drop apart. There's no AC voltage between them. And we'll choose the new capacitor so that it will look like a short circuit at signal frequencies. In other words, both ends of the capacitor will be at the same AC voltage. The resistor R3 therefore has both ends at the same AC voltage. It carries no AC current. At signal frequencies, it looks like an open circuit. So the only load that the input sees is the base of the transistor, beta plus 1 times the emitter resistor in parallel with the load. The input capacitor forms a high-pass filter with that impedance. And we can use a value about a quarter what it was before. I've got film capacitors that size on hand. No need for an electrolytic here. Another way to look at what's going on here is that the capacitor is adding the output AC voltage, which is the same as the input AC voltage, to the middle of the voltage divider. This feedback is a little strange. It's as if the circuit is pulling itself up by its bootstraps to raise its input impedance. And this technique goes by the name bootstrapping. You'll see the capacitor referred to as a bootstrap capacitor. I still didn't mention how I got the value to use for the bootstrap capacitor. R3 is an open circuit at AC frequencies from its end, too. So the only load the capacitor sees is the voltage divider. That forms a high-pass filter. Once again, we set the corner frequency an order of magnitude below the lowest signal frequency. This circuit is worth actually building and measuring. Off to the cave! Down here in the cave, I've made the last-minute decision to substitute a 27 kilo-ohm resistor for the 10 kilo-ohm one. All the better to show the effect of the bootstrapping. That's the source resistor, by the way. Otherwise, the circuit on the breadboard is exactly what I showed. I've got the voltage divider with its extra resistor. I've got the transistor with its collector on the power supply. I've got the emitter pull-down. I've got the output coupling capacitor and the bootstrap capacitor. When I turn it on, I see the output signal has lost about 10% of its voltage. Gone down from 6 volts to about 5.5. It's a little bit out of phase here at the bottom of the frequency range that we designed for. But when I pull out the bootstrap capacitor, the signal suddenly plunges to about half the voltage. Apparently bootstrapping works as advertised. You'll see this circuit used pretty often in a push-pull configuration in audio power amplifiers, at least the classic ones. A lot of newer high-efficiency ones use pulse width modulation instead, but that's a topic for another time. I think I can give the emitter follower a rest for now. I still want to get back eventually and revisit what to do when your transistor's beta just isn't big enough. But it's time to move on to looking at how much further we can get with understanding current sources and common emitter amplifiers. This episode was kind of an unintentional trip down the rabbit hole. Still, I think that doing this sort of detailed analysis at least once will pay dividends in the future. Let's see if we can't use what we've learned to take a few shortcuts next time. I hope you'll stay tuned. Stay safe, stay healthy, stay curious, and take care of one another. Bye.